Next, we move on to the project's significance and relevance. The agricultural sector is the backbone of the economy for a lot of rural districts in Malaysia. Therefore, it is crucial for us to find a relationship between economic growth and agricultural sectors in districts all around Malaysia, so that we can grow these districts to become economically sufficient.
For this project, we used two datasets. The first contained crop production by district, including crop type, species, and the production values. The second dataset provides GDP growth data by district from the Department of Statistics Malaysia. We focus on 2017 data to predict 2018 agriculture growth, aiming to analyze how crop production influenced district-level economic performance.
In the pre-processing phase, we comb through the dataset for not a number values for easier modeling. Next, we synchronize the date format to only the year for simpler processing in the data frame. Then we merge the year on the economic growth index to the dataset with their respective district. After that, we specify the data to only the year of 2017. And lastly, we focus the economic growth index only on the agricultural sector. So this is our coding for pre-processing, and this is our clean data that consists of more than 10,000 rows and 7 different features.
The first model that we trained is a linear regression. The steps is to scale the data, split the dataset, and fit the model. We use this linear regression to predict the values of economic growth based on the data points provided and plotting the graph. Based on the graph, the values are very inaccurate and has very poor fit. It is not a suitable model to find economic growth. Based on the evaluation matrix, the regression has a very poor fit, very low error because the dataset is large enough.
So the next model training is the Bayesian regression. I use this model to predict 2018 economic growth based on the crop production data from the 2017. However, as you can see in the graph, the predicted value mostly clustered around 0 and don't follow the actual value closely. The R-square is very low, meaning that the model doesn't capture the relationship well. So this suggests that this model is not suitable for accurately predicting district-level growth using this dataset.
So, for clustering analysis, we use the K-means algorithm in combination with PCE. First, all numerical features were standardized to ensure they contribute equally to the clustering process. And then we apply the K-means clustering algorithm with 3 clusters and PCA to reduce the data to 2D so we could visualize the cluster distribution clearly on a scatter plot. In the graph, each color point represents a district and the red S mark indicate the center of each cluster. So, the R-square score is 0.81 and the MSE is 0.19, implying good clustering compactness.
Okay, so for our fourth modeling, we use Gaussian mixture model clustering. So first, we prepare data by extracting just the production and value columns. Then after that, we train the GMM model by telling the model to find only 3 clusters in the data and assign each data point to a cluster. And then we create color scatter plot to show clusters visually and compare the actual scaled data points to their cluster centers. Also, we check how close they are using mean squared error and how well the cluster centers explain the data by using R-square. Here is the result of our project using GMM. So one cluster contains wide variation in production, possibly capturing outliers or high production records. The covariances matrices tell us how stretched or circular each cluster is. The cluster centers explain about 5.3% of the variances in the scaled data. Since the R-square score is very low, this model does not fit the data very well. And then the mean squared error is 0.9468, that is near 1.0, are not close enough to the actual data points to explain the structure effectively.
For the last model, we have support vector regressor. We perform hyperparameter tuning using C, epsilon, and also kernel use RBF to capture nonlinear relationships. So for the performance metric, we have value of R-square of 0.033, which is far from 1 and indicates low predictive performance. And for the mean square error, we have 35.83, which is high and tells us that it has large prediction errors present. And for the mean square error, we have 5.96. And scatter plot analysis, the green dots represent the predicted, which is actual GDP growth for the district, and the red dash line is the perfect prediction line. And based on the graph, the prediction seems to regress towards the mean, which tells us that the model unpredicts the high growth and overpredicts the low growth. And the model struggles to capture extreme growth, which results in underfitting. This is the comparison table for all triangles that we use. So since we are predicting, the best thing to do is regression. So the best evaluation matrix is R-square score, mean square error, and also root mean square error. So among all models, SPR show the best performance because its R-square, MSE, and also RMSE has better performance than others, and it also captures nonlinear patterns better because it uses RBF connect and also perform hyperparameter tuning.
In conclusion, the SPR model proved to be the most effective for predicting crop production because of the highest R-square score and the lowest MSE. As for recommendation, first, it is advisable to incorporate more relevant features to improve model prediction. Second, to update the model with new data to maintain accuracy over time. And last, to continue to apply hyperparameter optimization techniques for even better performance and robustness.